Welcome to Plutus IES. And today we are covering our last topic that we'll be going forward with throughout the discussion of reagent, that is called as your Cram-Chelate model. So in our junior classes we already know that what does the Cram model do. Cram model help us to determine when you are attacking a carbonyl which contains a asymmetric carbon center, what will be the stereochemistry of the attacking nucleophile. This we have used while studying in the pre-examinations of JEE and NEET. But now what does significance it holds when we are talking about in Cram model in terms of UPSC. So what does Cram does? It tells us the stereochemistry of the asymmetric carbon center after attack of the nucleophile, which can be directed by various factors. So previously we have known that from the Cram model that the nucleophile, if I go for a normal Cram model, we know, let's say this is our carbonyl group. This is some asymmetric carbon center. Let's say this is some R1, this is some R2, and let's say this is your H. And this is something here R. So here, this point right here, this our asymmetric carbon center. So let's suppose if I want to bring in a nucleophile to attack this carbonyl, so which side it will attack? From the frontal direction, from the back direction, that can be determined by using Cram model. So as per Cram model, the carbonyl carbon can be represented like this. This bigger circle represents the carbon that you have, while the oxygen is the group that is bonded to it. Now, we need to arrange these groups that are here around this carbon, which is our larger circle, in a form like this is our smallest group. Let's say this is some medium group, and let's say this is a large group. So if I make it, now we make this configuration in the form of staggered form to avoid steric repulsions. So here I'm taking what? I have made what? I had my smaller group here. Let's say some medium and larger group here. Now to avoid the repulsion from larger and the medium group, this R group will be opposite to these three. Wait. It should be medium, it should be large, it should be small, and here is the R group which is present in between these. So now I have the option. Let's say I'm bringing a nucleophile, let's say H minus, attacking a H minus. So now the option is either I can attack from this position or I can attack from this position between the medium and the small group. So the Cram model explains that to avoid the steric repulsions, this nucleophile will attack from the side of the smaller and the medium group, and this path would be preferred instead of this one. So let's say if this was an H minus, that means on red I'm doing the reduction of carbonyl. So it will give me what? It had some H, some R1, some R2. So it will give me an alcohol, and let's say some R group was here. So I added H minus. So what will be the configuration? Whether it will be at the wedge, whether it will be at the dash. So to avoid the repulsion from the larger and the medium direction, the H minus will attack from opposite direction. So in such case, the H minus, to avoid repulsion, will be far from these. Hence, it will be at the dash, while OH will be at the wedge. This is the condition that we know. So what does Cram-Chelate model does? Cram-Chelate, this was all about your Cram model that we already know. So now, what does the Cram-Chelate model does? Well, it is most used for hydride transfer reagent like ZnNH4, ZnBH4, NaBH4, LiAlH4, some Ru2O, such kinds of reagent. Now, What does it say? It says the reagents which contains metal center which are capable of chelation, they favors the they favors the carbonyl to retain its stereochemistry, to retain its stereochemistry stereochemistry. That means the attack will take place from the same side where the groups are present originally, while the reagent like NaBH4, LiAlH4 or some which involves potassium, these are your these three reagents are not capable of chelation, not capable of chelation. Since they are not capable of chelation, they will follow normal chelate model. Normal chelate model where the hydride or the nucleophile will always be present opposite to the larger groups. So in chelate model, we are doing an example. So in this case, let's say this is our atom, this is our molecule A, and let's say, wait, let me move them a little side. And this is our B. Okay, so what does एक मिनट पहले इसकी condition लिखते हैं. Wait, so let's keeping it side. So Cram-Chelate model has several conditions. It has two conditions. Number one, that alpha carbon of the carbonyl should contain a polarizable group. Should contain a polarizable group. Polarizable group, which can be in the form of NHR, can be in the form of OR, can be in the form of OH, etc. Second, the reagent that you are using, that metals which are capable of chelation are, you are using, if they are Cr3 plus, Zn2 plus, manganese, etc. While lithium, sodium and potassium like metal centers are not capable of chelation, hence we will not follow the Cram-Chelate model for them to explain the stereochemistry. Instead of that, we will follow normal Cram-Chelate model. So for the example that we have, in this you can see that I have attached a polarizable group right here. Okay, now if I'm using ZnBH4 and let's suppose I'm using let's say NaBH4, both reduces carbonyl to aldehydes. Sorry, this is a ketone, so both will be reduced to alcohol. So here the H present on the same side as the polarizable group, this is only possible as per Cram-Chelate model. Hence in this we get 95% of this product while only 5% of this. While in case of NaBH4, which is not capable of chelation, we get around 28% of it, while around 72% of this. So clearly we can see the difference right here. So this can be explained by using this. Okay, I've attached an electron withdrawing group, some R group, carbonyl, oxygen. So as per nucleophile, this is what? So I have my OR group, my smaller group H, which was here. This is my small group. This is my bulky group R. This is medium group, and this is your larger group. So when the nucleophile needs to attach, what happens? The ZnBH4 that you have added, it forms a 5-membered chelate ring, which is a very important factor while going for Cram-Chelate model. That whatever reagent you are using, they should be capable of formation of a 5-membered chelate ring. So here we can see that the chelate ring has been formed of 5-membered, which include number 1, 2, 3. Sorry, 1, 2, 3. Wait, 1, 2, 3. 1 2 attached to the carbon, 3, that should be 4. Wait, am I missing something? That should be 1 2 3. Oh, sorry, 3 4 5. Sorry, the oxygen will also be included. 1 2, that's 1 2, the second carbon. Okay, okay, second carbon. So this is a 5-membered ring. So what happens now? The nucleophile has to attack. So clearly the nucleophile will attack what? From the direction of H minus or OR minus, which are in this case, if you see. So here, since the zinc has withdrawn the electron density from OR group or from your carbonyl group, now the chances of attacking this H minus are far larger, not from this direction, but from this direction, are far larger than any other case. So in this case, the carbonyl will attack between the medium group and the large group, converting it to the CH form. This will later reduce to alcohol, and this is your hydrogen. Sorry, it will attack from this direction. Sorry, it will attack this direction between the small and the medium group to avoid repulsion. So after this, you will get this kind of configuration, and when you redraw it, it gives you a structure like this. So what does Cram-Chelate model does? It tells us whenever you are using a reagent which is capable of chelation, in that scenario, the stereochemistry of the nucleophile will always be similar to the medium group, which is also our polarizable group. This is what is meant by Cram model, that the nucleophile will have same stereo as the medium group. Medium group had, that's why we got H at this position, and in this case, this is what, that's why it was our major product here. Okay, so the important factor, we know that you should have at least you should have a metal center which is capable of chelation. It should form a 5-membered ring. Alpha carbon should have a polarizable group, and the stereochemistry will always be same as in the case of the medium group. So I hope all your doubts regarding your Cram-Chelate models has now been clear. In case of any further doubt, you can add it to the comment section and we'll get back to you. And thank you for joining us for today.